for you all of the really cool water activities and the Poggle that you just completed with everything in there. So big things that I want you to know out of there are truly the 5 universal properties for water. I would quiz yourself on these. I'd put them on a flashcard if this was my stuff. So um, let's start at the top with polarity. If you do not remember what polarity means or you've never learned it, here's your quick, easy guide to polarity. So when any two molecules bond themselves together and one comes from the right side of the periodic table and one comes from the left side, what happens is there's generally an uneven distribution of those electrons. One pulls harder on the other. It's a really big chemistry thing. Here's what you have to understand about it. It's uneven. Someone is pulling on the other person. I think of polar pull, and I put those two things together. You can see in all of the bottom examples on here, well, I guess both of the bottom examples on here, H2O and then that one on the bottom, NH3, or the amine group, that those molecules are bent in shape. The reason that they are bent in shape is because of their polarity, because there's some sort of an uneven distribution of the electrical charge in the molecule. Anytime there's that uneven distribution, it creates some really amazing properties that's in there. This is the reason water has the super cool properties that it has. On the other side are molecules that are nonpolar. This is also going to be an important concept when we get to cell membranes. You can see in the molecules that are over on that right-hand side in the nonpolar column, they're pretty much ones that are very even or they're very straight. And what I remember is nonpolar molecules do not pull on one another. All of the charge across there is totally even. In fact, disregard the bottom example for a moment. If you take a look at all of the both of the top two examples, you'll notice that both of those elements come from the same area on the periodic table. Typically, things that come from the same area on the periodic table will not pull on one another. They share their electrons nicely. They create a covalent bond. On the right side, they are coming from one on the right and one on the left, so they're unevenly sharing. It's an ionic bond, and they're pulling on one another. This molecule on the bottom, while it looks like it's a pyramid with one up to the top, and yes, it is, it also is evenly distributing that charge all the way around. It's kind of a cool, fun property about carbon is how nicely and evenly it will have everything balanced around it. And then in this case, you can see that there are 4 chlorine molecules. That's an even thing. So one on the top, think left, right, top, bottom. It's just going to pull evenly across all those molecules because it's all the exact same thing. If we had other funky people in there, that does do different things. But in this case, for that bottom chlorine to carbon molecule, because it's 4 chlorines, they oppose each other, one on the top, one on the bottom, and then the left-right versions. And so they end up being even and not having an overall pull on that particular molecule. In your Poggle, the polarity is in this read this section, and that's up at the very top on page 1, and that's what it was talking about. So you may want to highlight that polar molecule. Yes, it's in your textbook. Yes, I'm talking about it right now, but that's really where you can also go take a reference to that one. I like the diagram that's in there, then it's just drawn out for you. Textbook, again, great resource on polarity. If you don't fully understand the chemistry, it'll get you through enough of what you need. When we look at polar and nonpolar molecules, where this really matters is if you've watched some of the other lectures, and as we start to pull these things together, our carbohydrate molecules and our DNA molecule and the phospholipid bilayer, so that's what that last molecule out here is. Some of them are polar and some of them are nonpolar, and why that matters is the molecule going to be able to like twist in on itself, or is it going to stay straight? Is it going to let other people near it? Is it going to keep people away from it? So polarity is a really important molecule. As you look at these ones, give yourself a pause, see if you can figure out which one of those is a non-polar molecule, and then why would that be important? In the nonpolar molecule that you have in here, your cellulose is not pulling on one another, and then that DNA molecule that's in the middle is also not pulling. It has an even distribution of charge through the middle of it. that's really important because we need our DNA molecule to be really stable. Over on that right side, or the left side, depends on how you're looking at it here, this phospholipid molecule that you're taking a peek, that has polarity to it, and that's going to be really important when we get to our cell membrane unit, next unit. So just put that one in your mind, that the phospholipid bilayer has polarity. When you put those two things together, negative positives are attracted to each other. That is why water was able to do some of the really cool things that it was able to do. It will stick to itself, the positive to the negative and the negative to the positive. It's unlike any other molecule in the world. This is the only one that we know of that has the unique properties that it has, which is why we call it the universal solvent, which we'll get to in a little bit here. On this one, hydrogen bonding is also going to be super useful. What other biomolecules use hydrogen bonds to keep themselves together? DNA uses hydrogen bonds. Phospholipid bilayer is going to use some hydrogen bonds. Cellulose over on the side uses hydrogen bonds. And then if you'll notice, we have nothing in the protein category. There are no proteins that hold themselves together with a hydrogen bond. Just backing it up here a little bit, the bond that's formed in here, so like really driving in deep right here, his hydrogen bond, you might want to label that on your POGIL if you don't have one labeled somewhere in there, is a hydrogen bond. Notice they're not actually stuck together. They're just like really close together. And that's true of a hydrogen bond, which gives it some pretty cool properties because it does stick together. So it is a bond. That's what, to bond means, is to stick together. But also, it's not very strong. So that's kind of cool because we can just rip it apart basically anytime that we need to rip it apart. But as long as it gets really close together, it's like two little ends of magnets, and they just go and they just lock together really easily. But it's a really bad magnet. It doesn't hold anything per se, so you can't do a lot with it, and you can pretty easily take it apart. So hydrogen bonds are pretty important, pretty unique things that we use here. Moving forward to cohesion of molecules. So something else that is super fun about water is that it has these two properties called cohesion and adhesion. And this was the thing that you saw when you were putting the, when you were dipping the water that was in there. So the paper towel into the water, and you saw that the water comes up. If you took that capillary tube and you dip the capillary tube into the dot of water on your table and just goes, it like pulls up into the capillary tube. The reason that water is able to have capillary action and it does those things is because of the property of cohesion. Cohesion is when water sticks to water. Adhesion is between water and another molecule. So the paper towel and the capillary tube were both showing you that cohesion, adhesion part that's in there. How I keep cohesion and adhesion in my brain separate is that cohesion starts with that CO. So cooperate, company, anything that's there, you're all together and you're one single unit. So just water. So cohesion, just water, water to water. Adhesion, AD, adding something else in there. So if we're going to add extra molecules together and water to something else, and this is specifically how the water is stuck to, let's use the example right here, the wall of a plant. And how water is able to move up from the roots to the very top is because of adhesion. It adds itself to the wall of the plant, and then it walks its way all the way up. Specifically, it is adding itself. It's a xylem cell that is in there, and then it capillary actions its way all the way up to the top. So pretty cool thing in there. And then cohesion is also going to be a factor that is at play there. This was the kind of cool property. As you were putting drops of water onto that penny, you were able to see that it forms that big bubble because water wants to stick together, and it wants to stick together, and it wants to stick together. And really what you're doing is you're taking these hydrogen bonds and you're stretching and you're stretching and you're stretching them until all of a sudden they're just so far apart and they're weak that the magnet, because it's like not all that great, just gives up. And then it can't stick together anymore. So that is why that one was happening in there. The other cool one that was in there, kind of a mostly just a cohesion component that is in there, is the way that when water forms that surface, you actually can float things on the top. And this is why the paper clip, you could slide that onto the very top that was there, and then you could get it to float. Now, I totally struggle with this one. So if you couldn't get your paper clip to float, don't feel bad. For every time I've ever gotten the paper clip to float, 3 times it just falls to the bottom. Surface tension is tricky. It's hard to play with. It does enable that really cool water bug to be able to float on the very top of the surface and then to walk its way, because that bug has such nimble, light legs. It's able to distribute its surface, its like whole body surface area mass over top of the surface of the water and not disturb any of those hydrogen bonds, which I think is just absolutely incredible that you can have whole animals that can like just float on the top of that. Hopefully you found something other than this water bug that has some cool surface tension. I think this is probably the example that you found, but if you did find something else, I would love to hear about it. The other kind of cool thing about water is that it resists changes in temperature. So if you have ever gone to a body of water, you'll notice this most often if you go spring and fall. So if you go during the spring, you'll notice that, oh my gosh, it's still really cold, but like the air temperature is pretty warm out here. Why isn't the water matching the air temperature? This is like an early summer thing. So late spring, early summer. Go to the other end of that spectrum, go to the fall, and you'll notice that like, why in the heck it's like starting to cool down, but the water is still fairly warm. Like the water and the air temperature are like really close to the exact same thing. It's what makes the beach really not very fun to go to in the fall, because you are not getting cooled off by the water the way that you would want to. They're really close together. The reason for this is that water is really great at holding on to temperature. So if you think temperature is like how fast can we get the molecules to move, water takes a long time to get moving and to heat it up. And because of that long time that it takes to heat it up, it will hold on to that water really well, that temperature really well. It really gets going, and it gets going, and it does that really slowly. And then it also is really slow to get rid of all of that energy and to like calm back down. So it's hard to ramp up, and then it's hard to get it to settle back down. It makes water a great place for organisms to be able to live because the temperature is actually probably pretty stable. You'll know this if you ever look at ocean temperatures, especially in coastal areas, the water actually like stays in a pretty narrow range. We feel like it's pretty big in terms of its movement, but it's not. Water doesn't have a large change in temperature in coastal communities. The specific property that goes behind that is called specific heat. So specific heat is how much energy it takes for a gram of water to be increased in temperature by 1 degrees Celsius. And water just, it doesn't get holding on to, it doesn't absorb that energy from the sun very well, and then it doesn't release it very well either. So kind of a really special property for water. One that was not in your packet, so I want to just put that in there for you. The other thing that water does that's really kind of cool is it helps cool us down. So if you get really hot ever, mostly think like summertime, or if you're sweating, if you're exercising and you get really sweaty because your body temperature has gone up really well, you'll know that you get really sweaty and you have all that water that's all over you. That water is trying to cool you off, and it is coming out of your sweat glands on the surface of your skin, and is trying to help to remove the temperature off your skin. The way that that is working is it's the heat of vaporization, so it's able to absorb the heat off your skin and then convert it into a gas. So literally you are heating up your sweat and then moving it off. The reason that you get sweatier and sweatier and sweatier and sweatier is because your temperature is so high and your body is trying to compensate, and it's trying to like counteract that heat that you are producing. If you get too hot, as you know, you get really sick and you start to feel nauseous and you start to not feel well. It's because your body is literally shutting down. So your sweat, heat of vaporization, it's literally trying to help to cool you down. Other organisms have this as well, not quite the same. Dogs don't sweat, they pant, same for cats. So it's not an every organism thing. It is kind of a thing special to humans and other creatures that are able to excrete sweat or have a sweat gland. When it cools and it moves off your skin, remember that that's called evaporation. Literally the exact same thing that happens off the surface of the water is just happening off the surface of your skin. The fourth property that is super cool is ice floating on water. It is the only substance in the world in which the solid form is actually less dense than the liquid form. And this is because when you slow the molecules down in a glass of water, so those hydrogen bonds that are cruising around and they're being all liquidy and they're sliding past each other and they're cruising and doing their thing, when you slow those molecules down to just the right point, they actually lock into place. And they form this really beautiful crystalline structure, and you can see that here. And that really cool crystalline structure actually traps space in between. It's not really air, it's just kind of space. And then that lowers the density of ice. So if you've ever not understood why ice floats on water, it is a density thing. The reason it's a density thing is because as you slow the molecules down, those hydrogen bonds can form tighter and then they get to float. That is actually a really great property because if you know lakes, in the winter, they will freeze on the top, but did you know that they are not frozen on the bottom? And that's a really important property because in big lakes and big bodies of water that freeze on the surface, there's life that lives underneath there that continues on. It does go into a little bit of a dormant stage, so think like hibernation. Those critters are in there and they're moving. If that body of water froze solid, you'd lose everything in there and you'd have to restart that cycle from the beginning. That's not good for life. So kind of a fun thing that gets to happen. It's not just that ooh, the ice cubes floated on the water. Yay, that's fun. No, actually it's a life-saving property for large bodies of water that are just the right size large, where you can get that surface to freeze and then you can protect all the creatures that are underneath it. So yay for changes in density preserving life. And then last but not least, water is considered the universal solvent. The reason it's the universal solvent is because of those hydrogen bonds and the fact that a water molecule is fairly stable, 2 hydrogens, 1 oxygen, and it can just form these cool things called shells of hydration. So those hydrogen bonds are really nice. They'll take certain molecules and they, again, because of the hydrogen bonds, form that they surround the molecule and they wrap it in a little hug. And they don't let, so in the case of the little picture that you see right here, they don't let the salt and the water, the sodium, chlorine, they don't let them stay together. Each one gets wrapped in its own little hug. And it's actually called a shell of hydration. And it's really cool. And that's what makes water the universal solvent. It's the only liquid, it's the only substance in the world that will do that, that forms that hydration shell around every single molecule that you put into it. Now, not all of them do that. When you were dissolving the sugar in there, the sugar molecule does not break apart. And the reason the sugar molecule, here is your shell of hydration. The reason that sugar molecule doesn't form that shell of hydration is because a sugar molecule is not 1 part positive to 1 part negative. It's a whole bunch of sharing. So then that doesn't actually dissolve. So little part on there that I want to make sure that you understand, when you drop the sugar in there, it wasn't doing the same thing. So please don't confuse that one. Salt does it this way. That's why if you've ever done a glass of salt water and a glass of sugar water and let them sit for a really long time, you'll notice when you come back, the salt is all the way it's back and it's crystallized, but all the sugar water goes all the way away, because the sugar and the water really are mixing all together, and so then they all evaporate. Yes, literally the sugar goes into the atmosphere. The salt, because of these hydration shells, the way that this has pulled all the way around it, it leaves the sodium and it leaves the chlorine behind. The water pieces out, and then that sodium chloride comes back together and they stick together. The other molecule in here that's will form these hydration shells is anytime if you have something that is also polar. because water is polar, so they like to like mix together and work together on those pieces in there. Just a nice diagram, the one that comes out of your textbook. It kind of just shows you what that shell of hydration looks like, and you can see the water literally is surrounding that molecule. It kind of just gives it a little hug in there. Two more vocabulary words that were sprinkled throughout your packet, and they have really big implications, and we're going to use these words over and over again, so stick them into your brain the way that you are please sticking polar and nonpolar. Are these two called hydrophobic and then hydrophilic? So hopefully the two words that you hear out of there are hydro, water, and then the suffix is philic and phobic. Phobic, hopefully you already know as something that you have a fear of. And then philia is having an affinity for. So if you have a philia, you have a liking for something else, and affiliation, you are associated with somebody else. When you did the water and oil, if you've ever done that together, if you've ever taken a bottle of salad dressing and you try to shake it up, you will know that they don't mix together. The reason they don't mix together is because oil is hydrophobic. It doesn't like the water. Oil molecules typically are non-polar in there, so they don't have any pull, so they're kind of like, get away from me. Water and other substances, like the ones we've talked about before, hydrophilic, they have an affinity for the water, so they're happy to play with that water, and then they dissolve into that particular one. So philia, you like water. Phobic, hydrophobic, you don't like water. Just stick those two words in your memory bank. We're going to use them a whole lot come cell membrane. A lot of this has really big implications in cell membrane if you haven't quite figured that out yet. Just another really great picture. This one's going to be kind of a little like we're moving towards our cell membrane here. Not going to talk too much about this on here, but know that this is kind of where we're heading. So this is a little bit of a preview on here. The water is not allowed on the inside. It is only allowed to touch the outside. So the two blue can hang together and the orange has to stay together. And that is why cell membranes are the way that they are. It has actually everything to do with the polarity and the philia of those individual components on that molecule. We'll get to that one. Just a little preview there. Last thing is kind of a bonus part on here, and that has to do really with the pH. And the reason that I had you take a look at pH, yes, pH is important. There are pieces on there that I'm going to need you to know. The big piece another one of the big pieces I want you to know is that water is both an acid and a base. It is this beautiful, perfect molecule that is a balance between this thing called a hydronium ion and this thing called a hydroxide ion. If this one's a little bit past your head, skip forward in the video just a little bit. If this is not over your head, I would love for you to really have that understanding that water is this both acid and a base. The reason that water is an acid and a base is it does this dissociation reaction at an equal rate when it needs to, depending on what substance it needs to. And because it can disassociate and reassociate so smoothly, it ends up being the best, the only example of something that is both an acid and a base at the same time. There's nothing else that's both an acid and a base at the exact same time. You're either a little bit acidic or a little bit basic. Not pure distilled water, and that's why we have to use pure distilled water in so many of our labs. One, we want to make sure that nothing is in there having any impact, and we want something that is purely neutral. Water is the only substance in the world that is purely neutral, and it is because it floats between that hydronium ion and that hydroxide ion back and forth. Picking back up with everybody, this is a scale that hopefully you have seen before in your life. So we talk about things that are acidic, things that are neutral, things that are alkaline. Alkaline and basic are the same thing. We just have two different words for describing that same property. Alkaline is the more technical, proper term for it. A base is a perfectly acceptable term. Just alkaline is like the more perfect technical term that you will probably see in places. If you've ever heard of alkaline water, it's just a little fancy version of water. It's just a little bit more basic. Acidic water would be a little less. It would have a little bit of a lower pH that is on there. A big picture, what I really need you to know between an acid and a base that is on there is this amount of hydrogen ions that's in there. That's really and truly the only piece that I need you to like stick in your brain is right here, that sheer number of hydrogen ions versus the lack of hydrogen ions. Do not worry about the other pieces. The reason that bleach feels soapy, if you've ever gotten it on your hands, is because bleach has very few H plus ions that are in there. Water, we really, distilled water is going to be a perfect balance of H pluses and the other component in there. And then if you've ever touched like lemon juice, you don't even have to touch it. It has an odor to it. It has a very distinct smell to it. And that has to do with the sheer number of hydrogen ions that are present in that water. So that's really the big thing I need you to keep in mind, is a lot of hydrogen ions means acidic. A lot of, or very few hydrogen ions, that's what basic or alkaline is. Okay. 14 is the top end of the scale. It means basic. 0 or 1 is the low end of the scale. It means super duper acidic. Is there about 7,000 more things that are in there? 100%. It's really cool. If you love it, please, and you have the ability to go take a chemistry class, do it. Top level chemistry classes that are in there. If you got out of here, you're like, yep, I know the difference between acid and base. Thumbs up. You're good. That's what I need you to know for here. I am not going to sit here and play this one for you, but I want you to take a watch on that short. It is a YouTube short in there, so it is super, I think it's 90 seconds. Please watch that. Watch it about 700 times. Watch it until it sticks in your head. That video is what I need you to understand about pH. Watching it. If you need another recap, you want to see some cartoons, you just want to see it in a whole nother way, go to the notes, open this bad boy up, and take a watch on this video. It's the very last one. Or just go pop open a new tab, type in Amoeba Sisters, Properties of Water, watch it. They actually do a really great job. Yes, it's a cartoon. Yes, it's the same stuff we showed you in 9th grade over and over again. They actually do a really great job with this one. So I would highly recommend, if you want to hear it from a different person, see it in a different version, that you go watch theirs, because it's quite nice. If you have any questions, bring them to class. Anything that you don't understand, come see me. I'm happy to help explain any of these pieces to you.